So a question, what is the quiz exactly going to be on?
Solutions.
Solutions?
Yeah.
Okay.
The solutions chapter. All right, so let's continue related to solutions, and we're going to talk more about molarity today, so we'll kind of going together. So we talked last time about acids and bases, right? We looked at what they are. Don't recall these definitions. We looked at some reactions between acids and bases, and how we determine what's an acid and what's a base has to do with how it's acting in a particular reaction, not a property of the molecule itself. Then we looked a little bit about kind of the more practical side of acids. So what happens if you actually have a sample of acid? How do we determine if it's a strong or weak acid? Excuse me. So one thing we didn't really look at is how concentration applies to acids. So we'll look at that first. Now, acids, dissolve in water, and so we can use any concentration method we want to talk about acids. You can talk about a 5% HCl solution or 5% NaOH solution. You can talk about molarity. And in most cases, for what we're going to look at in this chapter, we're going to deal with molarity. We talked about how that's really helpful when you're looking at equations, because you can look at moles and you can look at how much of something is being used. And it'll also come into how we measure acidity of a solution. So one nice thing about concentration is, let's say we take some HCl. Let's say we take 1 mole of HCl and we dissolve it in water. So 1 mole of HCl in water to give, let's say, 1 liter of solution. Remember how we make these solutions? You take your volumetric flask, you start filling it with water, you add your solute, and then you fill it all the way up to that 1 line, and that tells you you have exactly a liter of solution. So if we have 1 mole of HCl in 1 liter of solution, what's the concentration in molarity?
One mole to 1 liter.
Yeah. So what's the molarity?
1.
1 mole per liter. Okay. So remember, molarity is moles per liter. So if we have 1 mole per 1 liter, then we have 1 molar HCl.
So is it always going to be 1 liter?
Right. Molarity is always going to be per 1 liter. So if we have less than a liter, we have to calculate, right, we have to convert what it would be to a liter.
So like on the lab, we have like for our lab, we use 10 milliliters.
Yeah.
So we would convert it to 1 liter.
So you would divide by 0.01 liters. Yeah, if you added something in 10 milliliters. So because HCl is a strong acid, when you put HCl in water, you don't actually have any HCl molecules. So remember that because it's a strong acid, HCl plus water goes pretty much exclusively to hydronium and chloride. So it breaks up, it ionizes completely in water because it's a strong acid. So that means that in acidic solution, you can also say that if we have 1 molar HCl, then we have 1 molar hydronium and 1 molar chloride. So by using moles in our concentration, we can determine the actual hydrogen ion concentration in solution. So keep that in mind for a second. That only applies for strong acids. If we look at something like acetic acid or HF, we can't say that because we don't break it up completely. We only break it up a little bit. And so to figure out actually how much hydronium is formed takes a lot of other calculation and numbers and stuff that we won't do in this class. You can do it, but it's not as simple as just saying, oh, you got 1 molar of this, and you got 1 molar of this, because the reaction is not complete. It doesn't break up completely. So that's one way that strong acids make our life a little easier when we're looking at figuring out concentrations, is we know that it breaks up completely. And so we can just carry that concentration over.
Can you like determine the molar concentration when it only gives you the percentage of that, like say 5% of HCl or H2O? Do we have to first get the moles?
Right.
But adding together and then converting to moles?
Right.
Like the grams?
Yeah, just like the example from that last lab question. So you would take the 5% and you'd make that 5 grams HCl over 100 milliliters of water.
Will you do one of them?
Yeah. So let's say you have 5% mass to volume HCl, and you want to know what that is in molarity. Remember, we were not given a particular amount of solution, so we can pick any number we want that's nice and easy. And since it's a 5% solution, that tells us 5 grams per 100 milliliters. 5 over 100 is 5%. Now, we could pick other numbers, but they wouldn't be as nice and even, so we pick 5 over 100. So to convert that into molarity, what do we need to do? How do we need to convert the units?
Convert 100 milliliters to liters.
Yep, we got to convert the 100 milliliters to liters. So what is that? Yeah, so it's going to be 0.1 liter. Right, 100 milliliters is 0.1 liter. Right. So if 100 milliliters is 0.1 liter. If you want to go through and do the conversion where you divide by 1,000, then go ahead. You should get the same thing. And what do we need on top if we want molarity?
Moles.
Right. So we got to figure out how many 5 grams is how many moles of HCl. So that we have to do a conversion using the molar mass. So it's going to be 5 grams and HCl, that's 35.5 and 1, so that's 36.5. So that's 0.137 moles of HCl. So we put that over here, 0.137 moles of HCl. So 5 grams per 100 milliliters is the same as 0.137 moles of HCl over 0.1 liters. So if we divide that out, that's 1.37 moles per liter, or 1.37 molar HCl. 0.137 divided by 0.1 is 1.37. So a 5% HCl solution is the same as 1.37 mole.
So that's the calculation we need to know.
It's not actually. We did this in lab, but if you look at the objectives on Blackboard, the mass to volume conversions are not in there. So.
Oh.
So you should, yes, you should be able to convert to moles. You should be able to calculate a molarity given moles or grams in a volume, knowing that molarity is moles per liter. But this particular conversion dealing with the 5% mass per volume is not, the mass per volume and mass stuff is not on the course objective, so we'll not have that part. Okay, so anyway, having said that, let's look at a really sort of strange equation, and then we're going to connect it to all the stuff we just talked about. What happens when a water molecule reacts with another water molecule? Does anything happen? So in pure water, is there any kind of reaction going on? Actually, you'd think, no, they're just water molecules. Why would there be? But in fact, in water, there is a slight amount of acid-base reaction happening. So two water molecules can actually react with each other to form hydronium and hydroxide. So one water gives the other water a hydrogen ion, and you end up with hydronium and hydroxide. And this is actually happening in water. So this is called the ionization of water, or the autoionization of water. It's ionizing by itself. And so pure water, it's not happening a lot. We know that pure water doesn't conduct electricity, so it's not a huge amount of ionization, but there is a little bit. And in fact, the concentration in pure water, the concentration of hydronium, which is given as this with brackets, when we put brackets around a formula like that, that means concentration of. So the concentration of hydronium is 1 times 10 to the minus 7th molar. So that's 0.0000001 molar. Like I said, pretty small. It's not ionizing completely. It's just ionizing a bit. And actually the concentration of hydroxide is the same. Because for every mole you form of one, you have to form a mole of the other one too.
Is this, does this have anything to do with surface tension and stuff like that? Is that why?
Not really,
this
no.
is different?
No, this is just something that happens in water. The surface tension is more controlled by the hydrogen bonding intermolecular forces. And this is a pretty small amount relative to the bulk sample. So most of water is just whole water molecules. But there's a little bit of ionization happening there. All right, why is that important? Well, this is actually how we can define whether or not a sample is acidic or basic. So we talked about looking at a molecule acting as an acid or a base. But we can also take a jar of something and say, this is acidic or this is basic. And we do that by measuring the hydrogen ion concentration. So if these concentrations are equal, like in pure water, we call that neutral. So when the hydronium ion concentration equals the hydroxide ion concentration, we call that neutral. If the hydronium ion concentration is greater than the hydroxide ion concentration, we call that acidic. So we have more hydronium, more positive ions in there. Well, not more positive ions, because there will still be other negative counter ions, but we have more hydronium than hydroxide. That's called acidic. And then if we have less hydronium than hydroxide, we call that basic. So let's go back up to our HCl example right here. If we have 1 molar HCl, that means that means that our concentration of H3O plus is 1 molar. So 1 molar is a whole lot more than 0.0000001 molar, right? So that means that HCl is going to be a whole lot more acidic in water than just pure water. Now we know that because we know it's hydrochloric acid, but this is actually what's happening to cause it to be acidic. We're adding more hydronium ion to the solution, and that's making it more acidic. Now, because these numbers are a little crazy, I guess they're not really crazy, but they're a little weird to work with because they're always these super small numbers with scientific notation. The pH scale was developed to help us deal with this. Does anybody know what the pH is?
It's the continuum between acid and base.
Right, so it's going to be a scale that covers the whole range between all acid or all base concentration-wise. And so it's going to be another way to measure hydrogen ion concentration or hydronium ion concentration. It's a calculation, and it looks like this. The pH can be calculated as the negative log of the hydronium ion concentration. What's a log? Remember back to your high school math or whenever you learned about logs. Nobody didn't been too long. Has anybody ever heard of that before?
Yeah.
Do you know that it was a thing that exists? Okay. It's a button on the calculator. It says log. Yeah. So log, I actually don't know where that word comes from. I suppose we could look it up. But it has to do with an exponent. Taking a log of something tells you what the little exponent is, the little number up in the corner. So a log of 10 to the minus 7th is minus 7. So the log tells you when you've got a number, an exponent that has a base of 10, tells you what that exponent is. A log of 10 to the 2, 10 squared, is 2.
So it's just gonna be the number.
So it's just that little exponent. Now, when you don't have a number as simple as just 10 to the something, like say it's 4.3 times 10 to the something, that's when we need to use the calculators to actually type in, okay, what's the log of this number? And it tells us what that exponent is. So what this means for pH is that we take our hydrogen ion concentration, we find the log, and then we flip the sign. That's what the negative is. So we go from negative to positive. Most of the hydrogen ion concentrations we're going to look at are going to have a negative exponent. So when we take the log, we get a negative number, and then we flip it to a positive number because the pH ultimately needs to be a positive number. So if we look at our hydrogen ion concentration up here, the negative log of 1 times 10 to the minus 7th is what? 7, right. And this is actually a unitless number. So we don't have any, it's not 7 pHs or something, it's just 7. So we took the exponent, the 10 to the minus 7, the minus 7 is the exponent, and then we take a minus minus 7, and a minus minus 7 is just 7. So this is where we get that pH of 7 is a neutral pH. Because at a pH of 7, the hydronium ion concentration equals the hydroxide ion concentration. So if that hydronium ion concentration increases, what happens to the pH? Goes down. Let's look, our previous example, 1 molar HCl. So that means that our concentration of hydronium is going to be 1 molar. So what's the negative log of 1? Well, we actually have to kind of write it in an exponent to see that. So what 10 to the what number is 1? Ten to the what exponent equals 1? No, 10 to the 1 is 10. 10 to the negative 1 is 1/10.
Should we just keep guessing?
Sure. 0. 0. That's it. So any number to the 0th power is 1. So 10 to the 0 is 1. So the negative log of 10 to the 0 is, the negative log of 10 to the 0. Remember, the log tells us the exponent. 0. Yeah. So that's the bottom of our pH scale. That means that 1 molar HCl solution should have a pH of 0. All right, so maybe go back home and break open that 8th grade textbook or whatever and refresh your log memory a little bit.
Can I ask you?
Yeah.
So what about things that don't break into H30 when you dilute them? I mean, not every acid is gonna give you that. If that's what we're.
It is,
measuring,
actually.
Every acid is gonna give you.
That's how we define an acid in water. Any acid that goes into water is going to give up its H plus to the water molecule.
So it's always gonna break into hydroxide and hydrogen, no matter what?
It may not form hydroxide, but it forms hydronium if it's an acid. If it's a base, it increases the hydroxide concentration.
But so every acid is gonna do that.
In
when it's
water.
dissolved in water.
Yeah.
But only in water.
Right.
So how do you determine the pH level of something if it's not in water?
Differently.
Okay.
Actually, the answer is you do it the same, but the scale becomes different because the neutral is not the water breaking up; it's some other solvent breaking up. So, okay. So the numbers then for our pH will be: if it's acidic, they'll be between 0 and 7, and if it's basic, they'll be between 7 and 14. So another equation that can help us is that the pH and the pOH added together always equal 14. That is the negative log of the hydronium concentration added to the negative log of the hydroxide concentration equals 14. So if the pH is 0, as in our previous example for 1 molar HCl, what's the pOH? 14. Another way we could say that is, what's the hydroxide ion concentration in a 1 molar HCl solution? Close. The pOH is 14, so the hydroxide ion concentration is 10 to the minus 14. Right? Because the pOH is like the pH, it's the negative log of the concentration.
So you couldn't just say 0.
You could, but you'd be
It
wrong.
would be wrong.
Right.
It'd be wrong.
Yeah, so you'll never have no OH. What that's saying is, even in the most acidic environment, you still have some OH formation from the water molecules, but very minimally. All right, so let's move on to some other examples of how we can use this. So one thing we can do is we can look at a scale for the pH and kind of think about what's on that scale. So we said that the pH scale, just lost it. The pH scale is going to go from 0 to 14 with 7 right in the middle. We're going to say pure water is right there at 7. 0 is going to be 1 molar HCl. 14 is going to be 1 molar sodium hydroxide, for instance. And then we have all this other stuff in between. So we can talk about relative acidity based on that pH. So what are some things that you would expect, just general things that you would expect in the acidic range of a pH scale? Actually, that would go the other way. Ammonia is actually basic around 12. So we'll put this one. Ammonia here, or bleach, it's about 12. So orange juice would be over on the acidic side, probably around 3. It's calling me from New York. Guessing that's the wrong number. So around 3, you also have, so you have maybe orange juice, soda, Coke, stuff like that is around 3. Nitric acid is another strong acid, so that should be the exact same as HCl. Remember, strong acids all break up completely in water, so one can't be stronger than another. They all have the same strength, so the same pH. So yeah, 1 molar of any of those strong acids would be here. 1 molar of weaker acids, like acetic acid, would go somewhere in here.
Any strong base is always gonna be 1 mole per liter in water,
Well, yeah, any strong base will break up completely in water, so you can
and will
assume.
always be 0.
Acid, you mean?
I mean, yeah, I'm sorry. it's-
Acid.
it will
So
always-
for 1 molar acid, we'll always have a pH of 0 if it's a strong acid, yeah. Yeah, because of the calculation, because of the hydronium ion will always be that.
Is the hydrochloric acid really strong? Or not?
It's not, no, that's considered a weak acid. Now, it's a very dangerous corrosive acid that will tear you apart, where we talked about that
Yeah,
last
I was
time.
Confused, the other day when we went over that, you didn't list it for strong acids.
That's right.
It's like, okay,
So remember, strong weak acid refers to its electrolytic capacity, meaning how much it breaks up into ions, not how dangerous or corrosive it is. So what that means is a 1 molar solution of HF would have a pH of higher than 1. It would be somewhere in here. But that doesn't mean it's any better for you, because there's lots of other chemical reasons that something could hurt you besides just how much hydronium it creates. Alcohol is kind of neutral like water, so we would expect those to be right in the middle there. Now, alcoholic beverages generally are on the acidic side because of other flavorings and stuff like that that are in there.
Then how come alcohol will make your blood more acidic? Doesn't it
I'm not
just
sure.
make your body more acidic if you're,
It could. That would have to do with what's called the metabolic acidity, with how it's actually processed. So the processing of alcohol, yeah, that makes sense, because the processing of alcohol in your body actually turns it into acetic acid. That's how your body deals with it. And so when you turn it into acetic acid, that's acid. So then that needs to be taken care of. And we'll talk a little bit about physiological pH in a minute. So since it's around Halloween, I always like to put up this table as well. pH of sour candy. So sour candy is always like, the dentist always says it's like the worst thing you can have, because below pH of 4 in your mouth, so your mouth is usually in a relatively just slightly basic state because of your saliva. So when you have acid below about a pH of 4, your teeth start to break down. The outside enamel of your teeth is vulnerable to stuff getting through it. It's decalcifying. And so if you combine that with sugar, that by itself is not great, but it's not so bad. It's when it's combined with sugar, which then feeds the bacteria that can get through the newly damaged teeth and start to get in and really cause some damage and tear stuff up in there. So anything that's going to have a pH of below 4 and sugar involved is going to be especially bad for your teeth. So that's,
Doesn't that include soda then? 'Cause it's both.
yeah. So soda has both, so that's why soda is so bad. It's pH about 3. Same with coffee or tea that has any kind of sugar or syrups or that kind of stuff in it. And then some of these candies get really acidic. So you figure stomach acid is a 2. And I don't know if anybody here has ever thrown up before, but you can kind of taste, stomach acid. It's not great. And if you do it a lot, it can really damage your teeth as well. And so there's actually a bunch of these candies considerably worse, like pixie sticks, that are actually more acidic than that, getting down close to the pH of battery acid, which is sulfuric acid. Yeah, I don't know. I haven't seen a lot of these candies, but I've definitely had some of them. Definitely taken down my share of giant pixie sticks as a younger person. So anyway, what did I say is you don't need to just stop eating everything like this or drinking soda. What you want to do is drink it in one sitting relatively quickly, maybe with a meal, so you get it all out of your mouth and it's not just sitting in your mouth hour after hour. Yeah, so you don't want to chew a sour gum that has sugar in it, or you don't want to sit there snacking on sour jelly beans or something, or drinking a soda over the course of an hour or two. You want to just have it done, and then your saliva can re-neutralize your mouth.
they did a study on soda drinkers,
Mhm.
people that drank like 4 a day, as opposed to one person who drank 1 a day, but they kept it and just sipped at it all day and they had more tooth decay than if you drank 4 of them,
Right.
Quickly.
Yeah, because you don't want that stuff to sit in and break down your teeth. All right, so let's talk a little bit about what happens then in your body. So this is this is obviously not good for your teeth, but inside your blood, this would be especially bad. So don't like mainline sweet tarts, for various reasons. But what? You quit doing that? That's good. So anybody know what blood pH is? pH of your blood? Yeah. So anyone who works in like monitoring this kind of stuff or in the health fields probably knows that number just from, seeing it on monitors and stuff. Is that where you knew it, or is it just something you had in your head? Yeah. So blood pH, it's a pretty narrow range. Think about that. That's not a huge difference in pH. And much deviation from that, you're really in serious trouble. Below about 6.8, cells can't survive anymore. And on the basic side, that's true as well. So your blood has to stay in a certain pH range, and you can really have problems if it varies from that. But we know that even a slight change in the hydronium ion concentration changes the pH pretty substantially. So your body needs to have mechanisms to control the pH so that if some extra acid does get into your blood, like through alcohol metabolism or whatever, you're not experiencing a shock to your system and a total change of blood pH. So anybody know how that does that?
Control, blood control.
Yeah.
Through nutrition.
It's through something called buffering. So we're going to talk about solutions called buffers.
And how can you balance that?
What do you mean?
How can you make sure, how can you test that?
Test the blood pH?
Aside from drawing blood, but for yourself, you can't.
Right. You need the blood to test it. So you can. There's monitors. You can put a monitor into your blood and test it that way. I don't think there's any way to do it without actually touching the blood and checking the concentration. Yes. So we'll talk about that. You can have acidosis or alkalosis, which is when your blood can be more or less acidic and can cause problems. So your blood does something called buffering, and a buffer is a solution that can control pH in a particular way, and it looks like this. Has anybody ever heard this term before? Buffer, like in terms of that, or just in like?
Yeah, like, oh yeah, buffering.
Buffered aspirin or like.
Right.
Pumps and stuff like
Yeah, so if something's buffered, it's controlling the pH. What? Yeah, not just when you're waiting for your porn, but or like shining up your chrome on your car or something. This is controlling the pH. So in a normal solution, let's say we've got some regular water, pH of 7. And we can do two things to it. We add a few drops of HCl, or let's say we add a few drops of NaOH. And really just a few drops. So a few drops of HCl will change that pH significantly. So that pH is going to drop down to maybe 2 or something, depending on how much water we have. Like a little beaker full of water, a few drops of HCl, that pH goes way down really fast. And then a few drops of NaOH goes the opposite. So let's say that pH jumps way up to 13. You put some strong acid or some strong base in there, it's going to change significantly what happens. Now let's say instead of water, we have what's called a buffer at pH of 7. Now you can make buffers at whatever pH you want. Let's say like in your body, so it would be a little bit higher than that. And let's say we do the same thing. We add a few drops of HCl or NaOH. With a few drops of HCl, our pH might change to something like 6.99. And a few drops of NaOH, maybe 7.01. So it's going to change a little bit. but the change is going to be so small as to be almost imperceptible. And in this way, the buffer resists a change in pH. So even with the addition of more acid or more base, the buffer does not change its pH significantly. And so it will eventually, if you add enough, but it will do a good job of controlling it within a certain volume.
Is it like absorbing? So
Yeah, so let's look at how it works. It's kind of like absorbing it. You make a buffer from a weak acid and its conjugate base mixed together. So let's say we made a mixture in equal amounts of acetic acid and the conjugate base of acetic acid. So here's like a little graph of how much of each thing we have. We'll make like a bar graph kind of thing. We're going to have two parts. So here's your acetic acid, which is HC2H3O2. And then for practice, what's the conjugate base of acetic acid? If that's the formula for acetic acid, what's its conjugate base? How do we find a conjugate base?
Take out a hydrogen,
Yep, take out a hydrogen ion.
HC2H2O.
Yeah, or we take off the first listed H is usually what we take off, but that's also correct. So that would be C2.
So it could be carbonated.
Yeah. But this way we see it better. That's why we put that H in front in the first place instead of just calling it C2H4O2. So we can show that it's an acid. So that's the acid, acetic acid on the left, and its conjugate base on the right, acid, which is called acetate. So let's think about what happens when we add some acid to this. So some acid is going to be H plus, and give it some H plus. Now, because this is a weak acid, it's not dissociating in water significantly. So if we add more H plus, it's going to stick on to the acetate, creating more of this, creating more acetic acid. So the H plus combines with this acetate and makes more acetic acid. So we end up with a little bit more acetic acid and the same amount of acetate that we started with. But note what we haven't done. We haven't changed the hydronium ion concentration of the solution. So that extra H plus coming from whatever acid we were adding, the HCl or something, didn't go connect with water and make more hydronium. It got kind of sucked up by the acetate and stuck to the acetate. And because it's stuck in that acetic acid now, it's not contributing to the pH because it's not making hydronium ion. So in that way, this is kind of stopped the pH from changing. It sucked in those extra hydrogens and stopped them from being in the broader solution and changing the pH. Similarly, if we add a strong base with hydroxide, that hydroxide is going to grab some of these hydrogens from the acetic acid. So you're going to have less acetic acid. And then you're going to have made some water from the OH grabbing those H's. But again, you haven't contributed to the hydroxide or the hydronium ion concentration of the solution. You're just messing with the molecules in the buffer. So in that way, it's controlling the pH. It's not allowing the strong or weak acid to mess with the water in the solution and mess with the hydronium ion concentration. So you're right, it's kind of like a sponge. It's sucking those extra hydrogens in and stopping them from contributing to the pH.
So I'm assuming that, there are supplements out there that regulate pH balance. Does it act as a buffer for as well?
Probably not. I mean, well, we'll talk about that. The major source of buffering in your blood is carbon dioxide. So carbon dioxide, which you form as a waste product of respiration, combines with water and forms carbonic acid.
Can you run?
Yeah, anywhere. So then carbonic acid we should make a separate reaction here. So carbonic acid combines with more water to form bicarbonate ion and hydronium. So this is the source of acidity. This is one source of acidity in your blood. But in doing so, you'll notice that you have now made a weak acid and its conjugate base. So these two molecules together in your blood create a buffer, just like the acetic acid and the acetate. And they prevent other acids that enter your bloodstream or bases from messing with your pH too much on one side or another.
So even though you're exerting out CO2 through respiration,
You're still always making more, right, to control that. Now, if that gets messed up, that's when you can cause some problems. So let's say you are hyperventilating. That's when you're breathing in and out really, really fast because you're, in shock or whatever. So you're breathing in and out really, really fast. What's happening to the carbon dioxide levels in your blood? They're going down. They're going down because you're exhaling too much CO2. It doesn't have time to get into your bloodstream. And so too much CO2 is getting out of your body. And if too much CO2 is getting out of your body, what do you think happens to your blood pH? Does it go up or does it go down? So if you're not getting enough CO2, what's happening to this equilibrium? It's going down because you don't have enough CO2 to complete this and make the appropriate amount of hydronium. So if you're pushing everything this way because you're exhaling all the CO2, then you're not getting enough into your bloodstream and your pH is going up. So the acidity is going down, but the pH is going up.
aside from obviously breathing too hard and that's, I mean, there's other ways where you also do that.
Right. So you can, the condition of your blood becoming too basic is called alkalosis. The opposite is acidosis.
That's losing your alkaline levels.
Yeah, alkaline is another name for basic. So it's the opposite of acidic. It's just another word for it. So if you hear anything being alkaline or whatever, that's talking about being basic. And if you, so if you're decreasing your CO2, then yeah, you're going to have a more alkaline environment in there, and you can actually cause problems that way. So what should you do, or what are some ways to fix that? You know, does anybody have hyperventilated a lot here?
Paper bag, you try and get more, you breathe into a paper bag.
Yeah, so you breathe into the paper bag, which your book has a great picture of that, which just looks like somebody throwing up. But they're saying, like, this is what you do when you're hyperventilating. So you sit down, you grab a paper bag, and now you're not getting rid of as much CO2 because when you inhale from the paper bag, you're sucking more of it in. Now, actually, this has been studied a bit, and they found that it's not actually the pulling back in of the CO2 that the paper bag is helping you not hyperventilate. It's just the fact that you're sitting and concentrating in your breathing. So it's almost like, yeah, it's like the paper bag is forcing you to stop and calm down and stop breathing so fast. And that's actually what's helping you. But when you calm down, you stop breathing so fast, you're not blowing off all the CO2. And so you are, your blood is becoming more in the standard spot. So you're right, there are other ways that you can have alkalosis, include from various diseases. Your book lists diseases of the adrenal glands, or if you eat too much basic stuff, it can get into your blood. We don't eat a lot of basic or alkaline foods because they don't tend to taste good. They tend to be bitter and kind of chalky or soapy. Some of the only ones we really get considerably or get at all are like things like cranberry juice. It's one of the only basic drinks that we drink, which is why it kind of has a different taste to it from other things. Baking soda is a little bit basic, and there are some like shortbreads and stuff like that that are made with sodium hydroxide or bicarbonate that are a little bit basic. But usually we don't get a lot of that, so it's generally a poisoning type issue if you're getting too much alkali in your diet. You can also have the opposite. So if you have too much CO2 and the buffers in your blood can't handle it, that's called acidosis. And this is usually a result of lung disease, meaning that you can't get your CO2 out, and so it's staying in your blood and it's not actually getting out the way it's supposed to, and that's increasing the pH. There's also, any other number of things. And then there's also what's called, so this is called respiratory acidosis. There's also what's called metabolic acidosis, which is things like you're talking about when you're metabolizing things like alcohol that are creating more acid and then getting that into your blood.
What is like CO2 poison, like carbon monoxide poisoning?
That's different. So that's carbon monoxide, that's CO. And that is, what happens with carbon monoxide is carbon monoxide binds tightly to the iron heme receptors that carry oxygen throughout your blood, and it binds tighter than oxygen. So when you have carbon monoxide, it sort of takes oxygen's place in your blood, and then you can't get the oxygen to your brain.
So it doesn't have anything to do with the abundance of carbon dioxide,
Right.
or just the lack
It's
of oxygen?
the lack of oxygen because the carbon monoxide is taking its place in the body. Yeah. So what else did I talk about? Oh, with metabolic acidosis, like alcoholism and other liver problems. So if your liver isn't metabolizing things properly, you could be getting more acid in your blood than you really should, and that can cause those sorts of issues. So.
So, like, if you exercise and you're breathing more, your body produces more carbonic acid, or I don't know, just like thinking that.
Well, yeah, I mean, it gets tricky depending on what the load is on your body. So if you're exercising, you're breathing harder, but you're also doing more metabolism in your body. So everything is happening at a faster rate. The bigger problem is when you breathe fast without that extra metabolism, now you've got more CO2 going out than should be. Because when you're exercising, you're creating more CO2, so you got to get it out faster. If you're just sitting there and you hyperventilate, then you're not making more CO2, so you don't want to get it out that fast. Yeah, is how I would think about it. I'm not a physiologist, obviously, but nor do I exercise. But that's how I sort of think through it. All right. So any other questions about that?
Joe, you don't lift?
What?
You don't lift, Joe?
Just cars.
Oh. This is all gonna be in the quiz?
No. So we're behind a chapter quiz-wise, which is why it would have been better to do the quiz today, but that's okay. So this will be, so the quiz is the previous stuff, the solutions, which we're still talking a little bit about solutions, but not specifically acids and bases.
Like the mass molar, like
The molarity and solubility and osmosis and dialysis, all that kind of stuff. From the previous chapter. All right, let's look at a couple of problems of what this stuff might look like, since we have a little bit of time here. Since it seemed like we're having a little bit of trouble with the pH stuff, let's look at a couple ways that we calculate that. So this is, we'll do just part of this. 10.74. So it's determine the pH for the following solutions. Let's do B. And then it says determine if these are acidic or basic. In each case, you're given the concentration of either hydronium or hydroxide and then asked to find the pH. So how do we do that for this first one? How do we find the pH of that solution?
pH 3.
It is not. So it would be 3 if the concentration were just 10 to the minus 3. But it's not, it's 4.2 times 10 to the minus 3. So in this case, this is going to be a calculator problem. Now you're right, we need the negative log of that whole number.
Which is 3.
So you would do -3 and negative.
So you do the negative log of 4.2 times 10 to the minus 3 to find, let me write this down here.
I thought we just took the.
Somebody want to punch that out for me? I imagine it should come out to 2 point something. Right?
2.38.
Okay.
How do you do negative?
Well, you can either just type it in like that, depending on your calculator, or you can just do log and then reverse the sign at the end. So if this were just 10 to the minus 3, then yeah, the negative log would be 3. If it were 10 to the minus 2, the negative log would be 2, but it's in between there. So 4.2 times 10 to the minus 3, another way of writing that is 0.0042. So the negative log of 0.0042 is 2.38.
So you just do it the same way you did a mole problem, like you just do it 4.2 and then second.
yeah,
and the E
right.
kind of-
What's the number on?
So the second one, there's an extra step here because we're not given the hydronium ion concentration, we're given the hydroxide ion concentration. So what we have to do is find the pOH and then subtract that from 14. Remember the pOH and the pH add up to 14. So the pOH is the negative log of 8.5 times 10 to the minus 9, which is what? Anybody do that one?
8.07.
So that means that the pH is 14 minus 8.07, which is 5.93. All right, so are these solutions acidic, basic, or neutral?
First one is neutral.
Why is the first one neutral?
No, it's acidic, 2.3, it's
Oh,
under
wait.
7.
Yeah, so if it's down under 7, we're going to call that acidic. So these are both acidic solutions. And on Monday, we'll actually measure hydrogen ion concentrations in lab using a variety of methods. We will look at pH paper, which is a paper that changes color depending on what the concentration is. We'll look at universal indicator, which is a solution that changes color when you drop it in your sample. We'll look at an actual pH meter, which is an instrument that you'll use to measure the exact hydrogen ion concentration in pH. And we'll look at litmus paper, which is a really simple, just 2-color system, red or blue, whether it's acidic or basic. Okay, let's do a couple where we go the other way. So this would be like 10.78. the question is, calculate the hydronium ion concentration and the hydroxide ion concentration for these various pH values. Actually, let's do D and E. So D is pH of 6.5, and E is the pH of 1.82. So if you're given the pH, how do you find the hydrogen ion concentration? Well, it's reverse of finding the log. The reverse of finding a log is raising to a power of 10. So we need, another way of saying this is, what number does the negative log of this number equal 6.5? So what number do we take the negative log of and end up with 6.5? That is 10 to the minus 6.5. You see how that fits in there? If you take the negative log of 10 to the minus 6.5, you get 6.5. Now, usually we don't have decimals up in our exponent, so that's how we use our calculator. We say 10 to the negative 6.5 equals what? What does that come out to? Can we calculate that out?
3.16.
Okay. Looks reasonable. So the hydronium ion concentration for this first one is going to be 3.16 times 10 to the minus 7 mole. Then how do we find the hydroxide ion concentration? Yeah, subtract the 6.5 from 14. This is all still that same question here. 14 minus 6.5 is 7.5, and that's our POH. Little p. That's our POH, like pH. So that means that the actual hydroxide ion concentration must be 10 to the minus 7.5, or how does that calculate out?
Uh, 3.16 times 10 to the negative 8.
Oh yeah, right, because it's just here. All right, so now we've got a hydronium ion concentration, hydroxide ion concentration. So see if you can do the same thing for part E. Different pH, otherwise should be done the same way. Yeah, so on whenever we do a quiz for this, I guess not next week, but the week after, make sure you bring in a calculator that has logs. If you're doing it on a phone, one thing I noticed on my phone, I don't know about your phone, if you're on the calculator thing, there's no log there, but then if you turn it sideways, the log pops up. So.
Troy does is giving me an error. On the phone calculator, mine says log 10. Is that?
Oh, yeah, that means, yeah, that's right. But I think on this one you have to push it after, so you do the number first and then push log.
You have to close to present.
Rather than putting log
Okay,
first.
so by following this is happening to its three.
And then log, and then negative.
No, the log is last. I don't know why they give you these calculators, because it's gonna be different for every calculator, but let me know. Oh, thanks, my computer's gonna
How
shut
did
down.
you get the 3.16? We don't understand that.
Yeah.
So we understand how you get the log is the 10
Yeah,
negative 6.5, but where did you get the rest of that equation?
yeah, I typed, well, I didn't, so I'm not sure it's totally right, but it looks right. But Nick typed in 10 to the minus 6.5 in his calculator,
And then
And-
just hit equal?
yeah.
Got-
and that's what you get.
Do you have to do 10 times negative 6?
No, 10 raised to the negative 6.5 exponent. I can show you what it looks like on, we can grab some various calculators and see what it looks like here. Switch the screen.
I'm trying to do the experiment on my phone.
So let's see, often, and every calculator is different, so we can, whoa. Here's what mine looks like. Can you see that okay? Kind of glare, but.
Can you use like a calculator? Use like
Can I use a real calculator? Yeah.
Oh.
I'll show you in a couple of different kinds. Can I take one? All right, so first on a fancy calculator. Hold on, I want to see the buttons too. So in the fancy calculators, you can type it in basically just as we've been doing. So I can say, hold on, I'm trying to get all the buttons on here. There we go. So I can say negative, if I want to do the log stuff, I can say like negative log of whatever these various ones are, 3.2 e negative 3. So that would be 3.2 times 10 to the negative 3. And that's then my pH, 2.49. To go the other direction, like we just did, we can say 10 to the minus 6.5, which is 3.16 times 10 to the negative 7.
Where'd you get the 10?
I just typed in 10. It's a 1 first and then a 0. There's
I meant like the exponent.
oh, the exponent is this little caret symbol here. There's also actually a 10 to the x thing here if you want to be fancy about it, but it's the same thing. Okay, so now we can look at this one. This probably does it the same way. Yeah, so the log is the same way. If I want to go 10, I'd go 10, and then I need to find the exponent. Somewhere here, should be, maybe.
Down the top.
On top?
Mm-hmm. Up. There, here's that one. The other
Oh,
one.
right here. 10 to the minus 6.5. Yeah, and there's 3.16 times 10 to the negative 7. Does that make sense? Do you see that? Does anybody have like a really simple calculator that is different? Yeah. Does it have a log on it at least?
No.
Okay. Oh, so it's even too simple for logs?
Yeah.
Yeah, so that one, you're talking about logs.
I know. What are you doing?
All right, so there are tons of these in the book to practice on, as well as examples in the chapter. I know it's confusing for those of you who haven't seen logs in a long time. But if you kind of look through the examples and practice it, I think you'll get it. It's the same procedure always, either negative log or something.
No,
Go ahead.
homework.
Yeah, is it not?
No, I didn't say anything.
It's not up yet.
It's not.
All right. Yeah, you guys gotta tell me that. It's supposed to be up, so I'll get that up right now.
Right?
Yeah,
You got to this weekend, right?
that's right. Until you got the quiz. So when do you want it to be due? Next
Let's do it next week.
next
So
weekend?
you're gonna put it up now, is it
Yeah.
any solutions too, or no, like with that or no?
What do you mean?
For the chapter that we just, the stuff that we just did, the
Mhm.
solutions, is it gonna be, is there?
Yeah,
Yeah, that'll help.
Okay. yeah. No, that's supposed to be up, so I'll put it up right now. Okay. I must have not hit the thing again. All right.
I can't even